Okay, before I get on to the lecture content this week, I want to just talk about one of the questions in the previous test because it deals with what are very important ideas that will come up again in the week 9 test and which are important for you to remember more generally because we'll be using them later on. So the issue here is about populations and samples. Question 8, you might recall, was about a confidence interval and a box plot that were published in a report by a university. The confidence interval was a claim about and the box plot about the years of work experience of alumni of a particular academic program, a degree. Now, in the original version of the report, it said that they took a sample of 20, representative sample of 20 alumni out of the 67 and calculated the confidence interval and produced the box plot. And that's the box plot there, and the confidence interval for the years of work experience is here, between 8 and 16 years. Then it was realised that there'd been a typographical error, that in fact that 67 should have been 670. So the first part of the question asked you, does the box plot need to be redrawn? Does it need to be changed as a result of that typographical error? Now, I think most people got this part right. They realised, I think they could see that a typographical error about the population size wouldn't affect the box plot. Not everybody, but the important thing to understand here is that a box plot is based here on a sample, the sample of 20, and nothing changed about the sample of 20. The error in the report was a typographical error. The sample was still a representative sample of the alumni of this program. It's just that they happen to be 670 of them, not 67. So nothing changes in the box plot. The box plot is a visual representation of the 5-number summary of the sample, not of the population of 670 alumni. And so nothing would need to change. Now, the next bit seemed to be a bit harder, so I think more people had trouble with the next part. So the next part was, should the correction to the report include a recalculated confidence interval for the median work experience of the 670 alumni? Now, in fact, the situation is exactly the same here. But this is where I think some people got confused, because what people seemed to say was that the confidence interval would have to be calculated on statistics or data from the population, and so it would need to be redone. But if you look at the formula there for the standard error and the confidence interval, and I hope you've memorized this because or you're very familiar with it, because there will be questions in the test tomorrow that require you to use it. The standard error is based on 2 statistics about the sample: the interquartile range of the sample, the third quartile minus the first quartile, divided by 1.08 times the square root of the sample size. There is nothing in that equation about the population. The population could be 67 or 670 or 6,700,000, would make no difference. All you're working with there is the sample of 20. And the confidence interval simply goes from the standard error by adding and subtracting 1.96 times the standard error to the median. That's all it does. So it's really important to remember that in statistical inference, and whenever we're talking about confidence intervals, we're in a situation where we're talking about statistical inference. We've got a population and a sample. And what we're doing is we're doing some kind of calculations with the sample, some sort of manipulation of statistics to produce a confidence interval for an estimate about the population. And there are many situations in real life where we don't even know how big the population is. You know, it's and we wouldn't know how to contact the entire population to even you know, collect information from them. So there are situations, for example, where you know, an example is you might want to know how many people in a city relied on friends or family for childcare. Give that as an example. Okay. Your population there, you might know how big it is. You might know which people exactly to contact, but you would have some ways of coming up with a reasonably representative sample. And then once you've got the sample, then you can do your calculations, come up with a confidence interval. So try to remember that whenever there's anything about an estimate that can be reported as, say, a confidence interval, then you've got a sampling and population issue. And as a critical thinker about data, and when you're using data for decisions, you should be thinking about what is the population and what is the sample, and is this, you know, can I be reasonably confident that the sample is sufficiently representative of the population for the estimates to be made. Now, we'll move on to the lecture component here. So what I've done this week is essentially, this is revision. We've made pretty good progress in the last few weeks, and I didn't want to overload this week too much because there's a test. So there's a bit of revision here, and we'll just go through it. In the test tomorrow, there are going to be questions that require you to make judgments and draw conclusions about run charts and, you know, box plots, and calculate confidence intervals for medians and proportions. So you need to be ready to roll with those things. So let's just go through it. So there's some housekeeping stuff here. I think you should be all familiar with this by now. Test 3 is this week. Hopefully you've all done the task write-up. I've spoken to several students now in the course of other conversations, and every one of them, I think, had done it. Didn't seem to have problems with it. There will be part of test 3 based on it. There'll be a couple of questions at least about the task write-up, and I'll be marking the task write-up as well. Canberra's now on daylight savings time. I hope you're all aware of that. So for some of you, that will mean the test, for example, will be at a local time that's different to the time previously. All right, so we start off with an update on COVID-19 cases. So I'm giving you updates of this from time to time, just to sort of keep reminding you of how run charts work, essentially. And in this version of the chart, this has the running median on it, and you'll see if we zoom in a bit on the last few weeks since our baseline, you'll see that things appear to be going up. So the running median is trending upwards, and you know, that's no doubt of some concern. But the health officials in Canberra are still saying that they're not too worried by this, that they still think this is this is sort of, it's not out of control. They haven't quite used the word out of control, but they've implied that. And they will be doing much more sophisticated statistical work than we're doing here, but I think they will almost certainly be using some sort of related methodology to get an idea of whether there are statistically significant trends occurring. So this chart was up to date as of, I think, the 4th of October. So I've made some observations about it. What has happened in the last whatever it is, 11 days or so, is we've had a number of outliers. So we sort of bounced above the outlier line, the upper fence line there, the red dashed one, but then plunged down below the control line, and then shot up suddenly. And I've talked in earlier classes about the sort of factors that have caused this. There have been some local clusters and so on. We had a couple of very high outliers there. There's an outlier just here. It's just barely an outlier. It's just above the upper fence line, and then there's 1, 2, 3 more outliers there, and then it plunged below. You will see this data again in the test tomorrow, but updated. And what else? Oh yes, I want to talk to you a little bit about some of the terminology here, because I think there's a little bit of confusion in the class about some things. So when I talk about a baseline, so baseline is one of the terms that gets used with run charts. And when we talk about a baseline, we're talking about a part of the data. So what we do with a run chart is we start with a slice, if you like, a time slice of the data, which we call the baseline. And what we want for the baseline is we want it to be pretty stable. We want it to be able to say, well, that represents a kind of status quo. Okay, the kind of reasonably stable situation. And what we calculate from that is the median. Okay, so the median of that period, that becomes the control line, this horizontal green line. And then what we're doing is we're looking to see whether there is a trend above or below that control line. So what we have after the baseline, so the baseline here is delineated by these 2 vertical dotted lines. The baseline, the data in the baseline we use to calculate we calculate its median, and then we use that to draw the control line. So we have the control line there. It's about 15 if I remember rightly, or 16 I think. So that's our control line, and what we're looking for is to see whether the median of the post baseline data is shifting above or below this control line. In other words, are things trending upwards or downwards from the baseline period? Now, I think one of the things that causes confusion is that the word baseline contains in it the word line. And so I think some students are sort of looking to see where the baseline has been drawn. The baseline is the control line. That's the median of the baseline data. Okay, so what we've learned about is some things that we look for in this post-baseline period. So one thing we look for is outliers, and as I've noted, we've got several outliers here. So that doesn't prove that there's a trend, but it's a strong signal, particularly if you get multiple outliers, that things are becoming unstable, that there's some change in the process going on. Now, in the case of the Canberra COVID, of course this was investigated, and it seems to largely be a matter of some fairly localized clusters of transmission. There was an aged care centre, and I think a couple of construction sites, and maybe something else. So you can be absolutely sure, and we know that the health officials have looked into those outliers very thoroughly, and they've come to the conclusion that these outliers are not representing a trend that's happening across the whole community. So outliers are one thing that we look for. Now, in this kind of data, we're not so interested in having outliers at the lower end, but in many situations we would actually put a lower fence line as well, and we'd be keeping an eye out for outliers at the lower end. The other thing we can do, and we looked at this last week, is we have a couple of fairly modern tests we can do. One we call the shift test, and another we call the crossings test, and we use them to test whether there is a statistically significant change happening. And if you get a positive result on either of those tests or both of them, then you can claim with about 95% confidence that the median value of the process has shifted. So the process here is the process that generates new COVID-19 cases. Now, with the data in its current configuration here, if we apply those tests, then what we actually find, and I think yes, we'll go down here to the next diagram. So this is the same diagram. I've just taken the running median line out there. So what you can, we use the running median there. That sort of smooths out the trend, and it gives us it doesn't prove that there's a trend, that there's a statistically significant trend, but it gives us a pretty clear idea of what seems to be happening. But you have to be careful with the running median because it's working with less data at the beginning and the end. Okay, in its current state here, it's you look at that and think, oh, maybe it's plateauing, but we don't really know for sure. That's probably drawing too much of a conclusion from the running median there. Now, if we go down just to make it a little clearer, this chart just contains the COVID-19 data. This is just the run chart. So what we see there is there are 30 data points after the baseline. Okay, if you count them, there are 30. Now, to conduct the shift test, we would need to see what we call a run of more than 8 data points, and to conduct the crossings test, we would need to see less than 10 crossings. How do we know that? Well, we look it up in a table. So let me give me a second. I'll bring up the table for you, and we can have a look at that. Okay. So this is the table that I've prepared, and what we need to do. So the number of post-baseline measurements is 30. So, and we're looking for the upper limit for runs and the lower limit for crossings. I'll explain those in a moment. So we go down to 30, and we see the upper limit for runs is 8, and the lower limit for crossings is 10. So what that means is if we find a run that is bigger than 8 data points, or if we see that there are less than 10 crossings in the post-baseline period, then we can draw the conclusion that there's been a statistically significant shift. So it's very important to remember that you're looking for more than, with the runs, more than 8, not 8, but more than 8, and with the crossings you're looking for less than 10 in this case. Okay. So, the largest run, let me zoom in a little here, and we can see what we're doing. Okay, so where's our largest run? So a run is a contiguous sequence of points which are above the median line, the control line, this one here. But we ignore points that are exactly on the line, on the control line. So the biggest run starts here. Okay. Now, how do we, well, strictly speaking, it starts here. It starts with this point. So we have, and remember we ignore points which are exactly on the median line. So there's a point there that's exactly on the median line. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, sorry. Let me start again. No, we don't. We have 1, I'll write numbers if I can. 1, 2, 3, 4, 5 there, and then it goes below the median line. Okay, so that's a run of 5 points. And we've ignored that one there. We've ignored that one that's on the median line. Now we'll look at the next run. Need to be a bit careful here when you've got outliers, because it's quite easy to get confused about the control line and the upper fence line. So here we have a run of 1, 2, 3, 4, 5, 6. So that's a run of 6, and we need more than 8. Okay, so that's only 6 data points. So that's not enough to make a claim about a statistically significant shift. That run would have to continue for another 5 points above the control line. Now, what about the crossings test? So we need less than 10 crossings. So we need to look pretty carefully here. So let's do this carefully. So the first thing is, there's our base. That's the vertical line there, marks the end of the baseline. So we don't count the first crossing there that comes after the baseline. We start counting the crossings here. So we've got 1 there, and then we've got 2 crossings there. It goes under and then over again. So we've got 2 and 3, right? Then we have another crossing here, so that's 4, and then we have a little run of 3 there, and then we have 2 more crossings, so that's 5 and 6, and then we have another 1, 2, 3, 4 there, so let's mark them. Okay, so that's 7, 8, 9, and 10. Now, what happens here? So we have a crossing here. It comes from down here, it moves up, crosses over and comes to there. So there is a crossing there. Okay, so that's 11. And then this is the tricky point you need to watch. So it goes up a little bit over the line there, and then it comes down to a point that is exactly centered on the line. So we ignore that one. That doesn't count as a crossing. You can think of it as sort of bouncing off the line. So it bounces off, so there's no crossing there. So this is all above the line, and then we have 2 more. So that's 12 and 13. And that's it. That's all the crossings. So we have 13 crossings, but we would need less than 10 to come to a statistically significant finding of a trend. Okay. All right. Let's just look at. Yes. No. That's all good. So make sure you understand how that works. Okay. If you need to go back over the recording and have a look, just do it, because it's a little tricky. You have to pay careful attention. And one of the things you've got to watch for, and you know, it could be being a little bit too fussy, but let's just to be strict about this. If you've got a point that is exactly centered on the line, then that is counted as being on the median line. But you may come across something that looks like that or like that. So that one is counted as being above the line, and that one is counted as being below the line. And if we drew a line between them, that would be a crossing, even though it's a very close crossing. All right, so that's, I think, everything I needed to say about run charts. But do pay attention to that, because it is going to come up in the test. Now, proportions. So we introduced this last week. There are going to be questions in the test about it. The point I wanted to make here, one point is confidence interval proportions are often wider than we might expect them to be. And if you've mainly, for example, been using confidence intervals for means or medians or whatever, and then you start doing proportions, you might get some surprises about how wide the confidence intervals are. So the first example here, these are just practice examples really. You should just make sure you know how to do these. Okay, so somebody in your organization has done a survey of 32 existing customers. We'll assume that that's a representative group of the customers, and 75% of them, 24 customers, indicated their intention to buy this new product that your firm will shortly be releasing. So your informant's happy because the business plan assumed a 75% or higher uptake by existing customers. Question for you is, how confident should you be about that 75% estimate, and assuming that it was a representative sample? So we just do the math really, remembering that we've got a population that we may not know how many customers there are all up, but that doesn't matter because we don't need that number. So there are 24 successes and failures. So the word success, when you're working in proportions, that just means the proportion that you're interested in. Okay, if you were interested in the proportion of people who die after operations in hospitals, then the deaths in hospital would be successes, even though they are tragic failures in real life. Okay, it's just terminology that gets used in statistics. So there are 24 successes, customers who intend to buy the product, and 8 failures. So the proportion is, the raw proportion, if you like, is 24 over 32, which is 0.75, and the sample size n is 32. Note that I've used lowercase n there. Doesn't matter. N is the standard symbol that is used for sample sizes, but sometimes people use lowercase and sometimes people use uppercase. There's no particular rhyme or reason to that most of the time. Now, the estimate we're going to use is this thing I introduced last week called the Agresti-Cool estimate, and we use that because it's basically a more reliable estimate of the standard error of proportions than the other one that's more commonly used. It's quite similar to the standard one, what's known as the Wald estimate. There's just a little adjustment we do up front. So the upfront adjustment is, there's 2 parts to it. We add 4 to the sample size, and then we add 2 to the number of successes. So the number of successes goes from being 24 to being 26. And so what we do is we calculate a new n, and we calculate a new p, a new proportion, and by convention they are signified by having a little tilde put over the top of them. Okay, so the new proportion is 0.722 rather than 0.75 after that adjustment. And then once we do that, we then use this formula here, which, square root of the proportion times 1 minus the proportion over the sample size. So you need to do that calculation. Be a little careful when you do it in the test. Make sure you show me your calculations. So if you make a minor calculation error, I can be a bit forgiving about it. And so you do all of this and you come up with a standard error. So once again, population, sample, the statistics that we calculate in the sample, if we are going to be estimating them for the population, there is going to be a standard error, and in this case you can calculate it. There's a formula, just as there is with medians. So once we've got the standard error and we've got our revised proportion there, so we use the adjusted proportion, not the original proportion here, that we use the adjusted one with a little tilde on its head, and we work out the confidence interval. Okay, and then once we've done that, we can say that based on a representative sample, we're 95% confident that between 58 and 87% of the population of customers intend to buy the new product. So that's a pretty wide, 58 to 87% is a pretty wide range compared to the kind of raw estimate of 75%. And that really was the point, one point I wanted to make there. So, you know, if you've never heard of this stuff and people start quoting proportions to you out of surveys, you might just take them on face value. If you, because surveys, even just simple little one-question surveys, are used all the time to gather information for decision making, and quite often that information comes as proportions. But if you're not aware of the standard error and for those proportions, they can be quite misleading. Okay, so that's one example. Then we have another example which is mathematically the same. It's just a different kind of context. So this is actually real data I found in a government report. I had to do a bit of work to kind of extract the numbers from it, reverse engineer them. But anyway, so this was about the report was sort of broadly about what people do with their assets when they retire, particularly the family home. So in this case, quite a bit of effort was put into trying to get a representative sample of retired people, and they were divided into age groups. And one of the age groups that was pretty accurately represented was people in the 75 to 79 year age group. And the issue at question here is, one of the things you can do at least in Australia and probably in many other countries, is if you own your home and you're elderly and retired, it's possible to take out something that's called a reverse mortgage. And what that basically means is you borrow money against the equity in your house, and you use that money to live on, or to live a better lifestyle, or to pay for healthcare, or go on cruises, or whatever. Now, but a lot of elderly people don't like that idea. They want to pay, they want 100% equity in their house, and they hate they've spent years paying off a mortgage. The last thing they want to do, emotionally at least, is take out a mortgage. So they did this survey, and they found that 86 of the 187 people in that age group in their sample said they would never draw down equity in their home for any reason, including medical or aged care. Okay, so that's a group with pretty strong views about this. So context here is you're interested in designing a reverse mortgage product, and you want to get a better understanding of what the attitudes are amongst potential customer groups. So to get something a bit better than just 46%, you want to get a confidence interval. So once again, you just do the calculations. So we've got, in this case, 86 successes. Now the successes are people here who don't want to be our customers, but they're the ones we're interested in this particular case. So 86 successes in a sample of 187. So the raw proportion is 46, and then we go through, we do exactly the same calculation. So we do the little aggressively cool trick here of adding 4 to the sample size and adding 2 to the number of successes. We get a slightly smaller, is it smaller? It should be. No, actually slightly, no, maybe slightly bigger, about the same. Doesn't make a very big difference in this case. Adjusted proportion, and then we do the calculation again of the standard error. We put in the numbers, we get a standard error of whatever it is, 3.6%, 0.036, and then we can calculate the confidence interval. And so the final result is, we can say that we are 95% confident that between 39% and 53% of the population of customers intend to buy the new product. Okay, so that original 46% becomes an estimate in the sample, becomes an estimate of between 39% and 53% in the population. Okay, we start with calculations from the sample, and we end up with a confidence interval, which is a statement about the population. Now, the final example here, this is an interesting little case, and this is a kind of situation where you can use the Agresti-Cool formula, but you can't use the more commonly used one, the one that's in all the textbooks, the Wald estimate. The So the context here is this is about fidget spinners. Some of you will remember these. There was a sort of a craze for fidget spinners a few years ago, and there was quite a bit of mass hysteria about these things. You know, they were going to destroy kids' education and so on. And then there was a counter to that, which was that some people believed they had therapeutic value for kids with attention deficit disorder and so on. A lot of talk about them. They're everywhere. But the setup here is you've got a school principal, and he's considering banning them in the school. Many schools did ban them. And he wants to get an idea of how many kids actually, have one of these things on their person or in their school bag or their desk or whatever on a day at the school. So he does one of the things you can do in this situation, which is you organize a random snap inspection. Okay. You randomly choose, in this case he chose 25 middle school kids and got them to empty out their school bags and went through their desks and empty out their pockets and so on. And lo and behold, he finds out that everyone in the sample has a fidget spinner. So that's interesting. So what conclusion can you draw from that? Well, you can't really draw the conclusion that every kid in the whole middle school, that's your population, I suppose, is the middle school, the middle school kids at that school. You can't conclude that everyone has a fidget spinner. Okay, you might have just been, kind of lucky or unlucky, depending on how you look at it, and picked a sample of kids where everyone happened to have one of these. But maybe there are kids that don't. So, but you can actually do the proportional calculation. So, and the calculation is done in exactly the same way as we've done the others. So, we have, what have we got? We've got, so the proportion is 25 out of 25. But if we adjust that, we've got to add 2 and add 4. So that becomes 27. What is it? 27 out of 29. So that becomes your P tilde. And then you can just go ahead and calculate the standard error, work out the confidence interval. And I'll leave you to do that as an exercise, but that's the confidence interval that you get up with. Now what, okay, so 0.84 to 1. Okay, so again, that's quite a wide confidence interval. It could be that, 16% of kids in the middle school didn't have fidget spinners on them. All right. Now, what you need to note in these kinds of extreme situations, some extreme situations like this, we have a term we use, we call boundary cases. And this is a boundary case. So what will sometimes happen with this proportional formula, when you do the boundary case calculations, you'll end up with a confidence interval bound, which is impossible. So confidence intervals for proportions have to be between 0 and 1. You can't have a proportion that is bigger than 1, and you can't have a proportion that is bigger than 0. If you actually go and do this calculation, you'll get an upper bound for the confidence interval of 1.023. What you have to do in that situation is truncate it, round it down to 1.0, which is what I've done here. Okay, and the same thing would apply at the other end. If you got say a confidence interval of minus 0.2 to 2.4 or something like that, it's impossible to have a negative proportion. So the minus 0.2 would have to be rounded up to 0. I'll just warn you that there's an example like that in the test tomorrow, so watch out for it. Okay, so that's it. So the key things to remember here, just make sure that you use the right formulas. Make sure you're thinking clearly about proportions and samples. It's it's a habit I want you to get into, because in real life, when you're in a working situation and you're dealing with data, you've got data coming at you from different sources. A lot of the time, the data is coming from samples. But the claims that are being made about the data, they are claims that are meant to apply to populations of some kind. And if you get into the habit of sort of instinctively thinking about, okay, what is the population here, and how good is the sample? How representative is it? How much effort was made to get a good sample? And knowing that it's a sample, there's going to be standard error for estimates. And then you ask yourself, okay, can we find out what that is? Have we been given the information we need to work that out? Now, for some statistics, and we've dealt with two now, we've dealt with proportions and medians, that's not hard information to get. It's not difficult to get. And it just turns out that there are relatively simple formulas that you can use to work out the standard error and work out confidence intervals. For a lot of other types of statistics, you can also do that. So for the mean, you can use the t-test, for example, so long as the data is the right shape. And for many statistics, you can use this technique called bootstrapping, which I've mentioned a few times. But what I really want you to get from this module of the course is this kind of critical thinking ability to think about, to spot when there's a population sample thing going on, and to think in terms of, standard error, and ask the right questions. So that was all. Good luck with the test, and I'll see you all in class next week.